AP Chemistry, and welcome to the last chunk of Chapter 5. But the last chunk of Chapter 5, we're going to talk about Hess's Law and heats of formation, which are two different ways to calculate the enthalpy of a reaction, right? So, going back to the stuff from the earlier in Chapter 5, right? Delta H is a state function, right? Since it is a state function, going back to those figures, that are all over your book, right? It doesn't really matter how we figure it out, right? It doesn't matter if we get from initial to final in 10 steps or 5 steps or 2 steps, right? As long as we know the respective energies of those steps, right, we can still come up with the same value for delta H, right? So, let's see. Oh, yeah, and that's why I put this figure here, right? Because it's the same thing, right? Where we can talk about the combustion of methane to produce CO2 and H2O, right? As being that, right, to produce liquid water, or we could say that it produces gaseous water, and then that gas to liquid releases some energy, right, and then the total sum energy is the same, right? That's what the figure is trying to say. All right, so let's go ahead and practice some Hess's Law, right? So it says that in 5.8, carbon occurs in two forms, graphite and diamond, right? The enthalpy of combustion of graphite is that, right? And we should, so again, this is one of those enthalpy of something, right? Enthalpy of combustion is defined as the amount of heat, right, to combust 1 mole of said substance, right? So in this case, it's 1 mole of graphite, right? That's why there's no coefficient there, right? 1 mole of graphite with oxygen. And that's its heat, right? And then we also have the other heat, right, for the combustion of diamond. And we would like to know the delta H for the conversion of graphite to diamond. Okay, well, so again, all we need to be able to do is get my final and my initial, final and initial being just our reactants and our products, right, in the right places, right? So if I want to go from graphite to diamond, right, I need to be able to get graphite as a reactant, and I can do that, right? So I have C graphite plus oxygen is going to give me CO2, and since I'm using that as written, this is negative 393.5, right? Now, I need to get diamond as a product, so I'm going to use that reaction backwards. So CO2 plus C diamond plus O2. Now I'm going to have to flip that sign, right? So plus 395.4, and I need to make sure that my reaction sums to what I need, right? So I have 1 mole of CO2 on each side, 1 mole of oxygen on each side. Those things cancel, right? Which means that my reaction now says C graphite to C diamond. So I have taken this one-step process and used these 2 steps to come up with its overall energy. So what that means is I'm just going to sum these 2 values. I'm going to take negative 393.5 plus positive 395.4, which will give me a positive 1.9 kilojoules for the delta H for this process. Yes, does that make sense? Another practice problem. So it wants the delta H for this reaction given the following information, right? So same thing, right? This is my initial, this is my final. I need to take the reactions that I have available to me and get everything in the right spot, right? So that's what we're going to do, right? So first we need some NO as a reactant, and this is the only place that we're going to get that. So we're going to take that as written. So NO plus O3 is going to give me NO2 plus O2, and since I'm using that as written, this is going to be negative 198.9, right? I also need to get O, just plain old O, atomic oxygen, as a reactant, and I can only get that here, right? So I'm going to take my 2O to make O2, and that's going to be negative 495 because I have to flip that, right? I only need 1 oxygen, not 2 oxygens, so that means I'm going to take this whole thing and multiply it by 1/2, right? And here, how you want to show that is kind of up to you, right? Depending on your level of organization, right? So for some of us, it might be helpful to go ahead and symbolize that somehow. So this is going to now be 1, and this is going to be 1/2, and this is going to be 495 over 2, right? As one way to do that, right? Just so that way we can try to keep track of what we're doing, right? Next one is that I need to make sure I have NO2 as a product. I already do. So then it's just about getting everything to cancel, right? So I still have this O3 molecule over here, this ozone, that I need to cancel. So I'm going to take this reaction. to get this ozone on the product side so I can get that to cancel, right? So this says 3/2 O2 is going to give me O3, and I had to flip that, so this is going to be plus 142.3, right? And now we got to double check, does everything cancel, right? So we have one NO and one O, ozone cancels. We have 1.5 oxygens, the 1.5 oxygens, those cancel. And so I do have NO plus O gives me NO2, which is exactly what I want. And I will then sum these, right? So negative 198.9 plus negative 495 over 2 plus 142.3 to give us our overall delta H for the reaction. Yes? All right. Next up, let's talk about heats of formation. So kind of like with oxidation states, there is just some foundational stuff you have to commit to memory so that way you can then do all of this, right? So one is the definition, right? Standard heat of formation. When we say standard, right, this means by definition 1 atmosphere if it's a gas. It means 1 molar if it's a solution, right? And it means that we're talking about 298 Kelvin, right? Formation is by definition, right, forming 1 mole, right? Only 1 mole from reactants, from elements in their standard states, right? So make sure that we've got that straight, right? It's always going to be to form 1 mole from its constituent elements. Other things that we should know, right? So if we're talking about the heat of formation as being the standard of how much energy is required to make 1 mole from its elements, then it stands to reason that there are a certain set of things that are going to have 0 heat of formation, because that's literally how we find it in nature. So it is, if we're talking about these as standards, right, we're going to consider that like the 0 point, right? So standard states we should know, right? Metals are solids except for mercury, right, being a liquid. So as long as a metal is a solid, that is its standard state, right? These are our gases that we should know, right? That's our other liquid. That's a weird solid that we should know, right? And the standard form of carbon is graphite versus diamond, right? So those are elements in their standard states. And obviously the heat of formation of any element in its standard state is 0. Okay, so let's do a practice. It says write the equation corresponding to the standard enthalpy of formation of liquid carbon tetrachloride. So it's going to form 1 mole of carbon tetrachloride, liquid, right? From its constituent elements. Its constituent elements are carbon in the form of graphite plus Cl4, so it'd be 2 Cl2 gas, yes? Because it must be from its constituent elements, and that would be a standard enthalpy of formation process for CCl4. And so if we were to look here, no, they don't have carbon tetrachloride on here. So then whatever the delta H for that process is, it would correspond to that, right? If we're looking at this table of our standard heats of formation, right, we can do the same sort of thing. Like, so for ammonia here, this is negative 46 delta H of formation is equal to negative 46.19, right? And so what that means, and this is kilojoules, and this is for NH3 as a gas, and so that is forming that from its constituent elements, right? So that would be N2 plus H2, and then we would have, these would be gases, and we would have to put them in the right proportions, right? So we need 1 of these, so it would be 1/2 N2 plus 3/2 of H2, yes? And that's what would get us what we need. Does that make sense, right? And it is one of the few times where it is common to see fractional coefficients, because by definition we need to produce simply 1 of whatever our product is. Yes? All right. Now doing some other practice. So here it says using heats of formation to solve for heat of reaction, right? So if we have a reaction that we would like to know the enthalpy of, and instead of having a series of reactions to work with, right, all we have is this, right? So again, it's about assessing what we have and what we need. In order to come up with our heat of reaction, we would take the sum of, that's what that part is, sum of heats of our formations times their respective moles for each. And this is the same thing for my reactants, right? And if we think about that, that should make sense, right? Because if this is the heat of formation, right, to produce this in the forward direction, right, then that means if it's a product, we would use that value as written. And if it were a reactant, we would have to basically use the flipped version, which is why it's, oh, that should say minus. Ooh, that's bad. Let's pretend. Products minus reactants. Yes? Fantastic. All right. So, moving along, it says use table 5.3 to calculate the enthalpy change for the combustion of 1 mole of ethanol. So we use products, so we'll start here, minus reactants. So it'd be 2 times our CO2 gas. So we would go find CO2 gas, which is negative 393.5. So negative 393.5 kilojoules. And remember that all of these are like technically per mole reaction, right? So really this is like per mole of CO2, right? And there are 2 moles of CO2. And that's why those units work the way that they do, right? And we're going to add to that our 3H2O, so 3 times our H2O liquid. So we would go find water as a liquid, and that's negative 285.8, right? And this is our, this part, right? Nope, that's our this part, sorry. And then we're going to do product minus our reactants, so turns out this one is easy, right? Because that's 3 oxygens times 0, right? And then we're going to add to that 1 times my ethanol. And ethanol liquid, negative 277.7. And this math is what's going to give us the enthalpy change for the combustion of 1 mole of ethanol. Yes? Makes sense? All right. Use table 5.3 to calculate the standard enthalpy of formation of CuO, right? So here it's a little bit different in that here, this is my heat of reaction, right? So this is our, what goes outside, and this is going to equal, right, everything else, right? Where we would still do products. Cu solid, that one's easy, right? Because that's going to be 1 times 0, right? Plus 1 times water liquid, right? Which we already did. What is that? 285.8, right? And then it's going to be products minus our reactants. We've got that 1, 0 again, right? Plus my Cu solid. So 1 times CuO, right? And then we can use that to solve for that, right? So just like any other math equation, right, which you guys have been doing for forever, right, we can solve for whatever piece it is that we don't know using our equation, yes? So heat of formation, to find heat of reaction, is always going to be products minus reactants. All right, so again, this part of chapter 5, so all of chapter 5 revolves around the concept of enthalpy, and what we're going to do is we're going to tie that into some other thermodynamic quantities in chapter 19, and all of it's going to come together. All right, thank you for listening, be good, and I will see you soon. Bye.